statement that you're going to, or the first type of statement that we're going to look at is called a conditional statement. By definition, it's a logical statement with a hypothesis and a conclusion. Now notice the words hypothesis and conclusion are written down below as well, so we'll kind of go into a little more details of those as we're kind of looking at this. But a hypothesis is going to be designated using the letter P, and a conclusion is going to be designated using the letter Q. Now sometimes these can be hard to distinguish when you're seeing them typed out, so just look carefully, make sure that you see the P or the Q. A conditional statement is an if-then statement. So that's another way to look at it. And if you look over here where you have this statement, if you are able to open a door, there's the hypothesis, then the door is unlocked. That is the conclusion. So the hypothesis is the if part of the conditional. And again, that will be represented with a P. And then the conclusion is the then part. Of that conditional. And once again, that's going to be designated with a Q. Okay, so another way that you're going to see these logic statements are written is with some symbolic representation. And what you will see instead of the if-then, a conditional statement is going to be represented as if P, then Q. This is the designation for that. Okay, and again, it will be read as if P, then Q. Okay, so if some set of conditions is true, then some conclusion is reached. So when you look up at this example, if you are able to open a door, then the door is unlocked. Now, conditional statements, when you're stating them, it is possible to find ones that are inconsistent or untrue. Okay? Most of the time, you're going to see them in or as definitions or theorems that are proven in geometry. But the validity of a statement is sort of somewhat irrelevant to the way that it's formed. Okay, but this is, if P then Q is set up in that symbolic notation. And so the hypothesis is the part that is the if part. So you are able to open the door. Okay, so that is the hypothesis. And the resulting conclusion would be that the door is unlocked. So the first part of what you're going to be asked to do is just to identify the parts of a conditional statement. Okay, you're then going to be asked to take that statement and make some slight adjustments to it by either putting negations, embedded in negations in the statement, or to flip the order of the hypothesis and conclusion, and you get different type of statement. And that's what we're going to look at here in this second slide. So this is the kind of the majority of what you're going to be looking to do. Is add some slight modifications to these statements. So one modification you're going to enter is negating the statement. So a negation just means the opposite of. Now, most of the time, this is just going to be in a single statement like this. It would just take P, like the hypothesis. It is Saturday, and the negation to that is symbolically represented as not P. This little symbol right here, which is called a tilde, it's called, or it's used in the geometry as a similarity symbol when we start looking at similar figures, but that represents not P. Okay, so that's the negation of whatever the hypothesis is. Okay, so if we just look at this hypothesis is it is Saturday, we see that it is not Saturday. That's the only part that's changed. This would be referred to as the negation. Now, it's part of, if you have the whole statement, it's not Saturday, uh, um, or if it is not Saturday, then you mow the grass, which is, would be the adjustment to that. That is still a negation. It's only taking the opposite of that original hypothesis. The majority of what you're going to look at are these last three new statements that can be formed, okay, by making some adjustments. The first is an inverse. In an inverse, you're going to negate both the hypothesis and conclusion. So in an inverse, what you're going to do is you're going to see the same order, P and then Q, but it's going to be the negation of this. So it's going to be if not P, then not Q. So that's sort of the symbolic representation for this. And the wording is if not P, then not Q. So that would be the logical pattern for an inverse. And so if you look here and you compare to the hypothesis and conclusion, and you see that there's two negations. There's a negation in the hypothesis and a negation in the conclusion, but they don't switch. That would be an example of an inverse. Now, if you take the hypothesis and conclusion and you actually switch them, that's called a converse. And so if you exchange the hypothesis, the original conditions, with the conclusion, then you get this converse. And so the converse is going to be if P, then, if Q, then P. So now we switch that order, right? So now it's if Q, then P is the converse. This is the one that we'll probably see the most. It'll show up in what are called theorems in geometry after you demonstrate something. Oftentimes the converse will also be true. Here's an example of it. If you mow the grass, then it is Saturday. Notice that it is Saturday gets moved to the conclusion. If you mow the grass, gets moved from the conclusion to the hypothesis. When you exchange those, this is an example of converse. And then the final statement modification that you're going to see here is going to be a contrapositive. And a contrapositive is going to do both the inverse and the converse. It's going to negate each of the statements. It's also going to exchange them. And so the way to kind of easily describe that is you're just going to take the negation of the converse. If not Q, then not P. And so that's the interpretation of the symbols and what the contrapositive is definition-wise. When you look at the example, you are going to see the negations in both the hypothesis and conclusion. You're also going to see that from the original form, they get switched or exchanged. So the mowing the grass, not mowing the grass is written first. It is not Saturday is written second. And that's the example of this contrapositive. All right, so this is, when you're identifying these, this is something that can be relatively easy to do using your notes, but if you don't make the effort to sort of memorize and learn, or connect it in a way that makes sense to you, it's going to be much more difficult to do this on the test when you don't have, or in your quiz when you don't have access to your notes. So on the homework, obviously you'll kind of learn it as you go, but be prepared to find a way to connect which is which. Right, the final slide, again, just a couple things that will fall in the vocab for this section. An equivalent statements are ones where you have a pair of statements that are both true or both false. They're equivalent to each other. Again, the validity of a statement is irrelevant to like what it's called or how it's structured. Okay, but if you do have two different statements and they're either both true or they're both false, then they would be equivalent to each other. And then the last sort of definition here to look at is something called a biconditional statement. You've probably heard of this before, but using a different phrase. Okay, biconditional statements are ones where the statement and the converse are both true. Okay, so even more specific than being equivalent, they both have to be true. And the way that you are probably familiar with this is set up as an if and only if statement. And so this is what a conditional or a biconditional statement looks like. And here, if P then Q is the original part. The converse of that would be if Q then P, but rather than rewriting this, if you see the arrow pointing in the other direction from Q to P, that is the symbolism for biconditional. Okay? It goes in both directions. If P then Q and if Q then P, they're both true statements, then you have that relationship. And so the wording is P is true if and only if Q. Now, oftentimes a biconditional we will see this in some of the theorems, some of the proven relationships later on in the year, but it's also apparent in some definitions. And so if you have the following definition. If two lines intersect to form a right angle, then they are perpendicular lines. Okay, so this is sort of a definition for perpendicular lines. Okay, the symbol for perpendicular is exactly what the definition is representing. So if you have two lines, so here's one line intersecting another line, and it forms a right angle, that means that these two lines, we'll call it line 1 and line 2 here, are perpendicular to each other. Line 1 is perpendicular to line 2. And you can see from what we've talked about, if two lines intersect to form a right angle, there's the hypothesis. Oops. Then they are perpendicular lines. That is the conclusion. Okay? And if you looked at some of the other like manipulations of this, okay? If we take the converse, if two lines are perpendicular, then they intersect to form a right angle. Both the original statement and the converse would be true. And so you could have also said by definition that two lines intersect to form a right angle if and only if they are perpendicular lines. So you can combine like these kind of statements here will be combined into what you will probably know more as definitions and theorems later on.